We are recording. Welcome to the evening of Python coding. I'm Jacob. I've been hosting this meetup for a long time now, and each time we bring a demo of a different Python tool or library. Today we have Sam Friedman, who's going to talk about about a library called passpredict that basically tracks satellites or predicts where the satellite should be. And I'm using the word predict, and I'll tell you later why it's unusual. Sam, please present yourself and tell us more about satellites and prediction.
Thank you, Jacob. And thank you for allowing me to talk. Hello to the Austin Python meetup. Hello to the DC Python meetup. I've been a long time observer, both in person before COVID and now virtually, of the Austin Python meetup. And I'm just really excited to be part of this community and show you guys this side project that I've been working on for a couple of years, something that I'm really interested in. I call it passpredict. It's a tool, a Python library to predict when a satellite is going to be directly overhead of your location on Earth. So this is how to see a satellite in your backyard. This passpredict library that I created, it's a tool to compute a satellite overpass for a specific location on Earth. And it includes a command line interface for quick predictions from your terminal, should you choose to find out when the space station is going to be over your house. And it's available on PyPI with a pip install passpredict, which I always like because it's just so simple, rolls off the tongue. And a little bit more about myself. My name is Sam Friedman. I'm currently a final year PhD student at Texas A&M. My research is in uncertainty quantification in coupled multidisciplinary systems. What that is statistics applied to engineering design projects. So it's heavily involved in scientific computing and using distributions, probability distributions to analyze physics-based simulations. And I just started as a software engineer at Hawkeye 360, working on their space software team. But this is my passion project. It's something that I've been working on for many, many years, and I'm really excited to share it with you all. So, first question, why would someone want to even know this kind of information? Just judging by the past Austin Python meetup libraries and things that have been presented, I can see that satellite predictions is a very niche problem, right? It's very specific, it's very unique. Not everyone even knows that you can find this information out. So who would want to know, and why would they want to know when a satellite will overpass their location? Well, just for fun. This is how I started. You can go outside and see a satellite with your naked eye, just looking up at the stars. If you see a star that isn't blinking, so it's not an airplane, and it's moving very fast, so it's not a planet and it's not a star, it's probably a satellite, or it could be a satellite, depending on a few other circumstances. But in particular, you can see the International Space Station in bright cities. The ISS is about 100 meters across. It's much, much larger than any other satellite in outer space right now. And it has these huge solar panels that reflect a lot of light. And even where I live in Austin, Texas, which has a lot of light pollution, if the conditions are right, you can see the International Space Station. And I'm positive you can also see it in Washington, D.C. You can also, if you're so inclined, view the Starlink trains after they launch. So for SpaceX, their Starlink satellites, they get launched in clusters of 50 to 60. And soon after they launch, you can see them almost like pearls in the sky before they reach their final altitudes and orbits. And they're visible if the conditions are right. And for the past couple of years, there's a group of people that love to see the Starlink trains because it is, I haven't seen them myself, but I can imagine that it's pretty unique to see a string of pearls in the sky that you can know are satellites orbiting the Earth at 15,000 miles per hour. Story time. So I live in Austin, Texas right now, but I used to live in San Antonio, and I was at University of Texas at San Antonio. This was in 2013, and my brother was living in Austin, in Central Austin. And at the time, I was interested in looking up when the space station was going to fly over me, and I knew that it was going to sort of pass San Antonio at this pretty close. This would be an example of what we would call the ground track, so directly underneath the satellite. And I was here at this blue marker, and my brother was in Austin at this orange marker, which is about 80 miles apart as the crow flies. So I called him up and I said, go outside in 3 minutes, look to your southwest, and if you'll see a very bright star, that's the space station. And so I was on campus at UTSA. My brother went outside in his backyard, and we were on the phone, and I didn't quite know what it might look like, but I knew it would be bright. And then eventually I saw it. And then 2 seconds later, he said that he saw it at the same time. And to me, when you see the space station for the first time, especially when it's a very bright, very visible overpass, it is magical in a way. I almost wanted to stop the other students on campus at UTSA and just say, everyone stop what you're doing and look, there's a satellite in the sky that you can totally see, and has astronauts on it. It's a great chance to be nerdy, and yeah, so that's why you might want to see it just for fun. I highly encourage, if you have young kids, to get them interested in science and space, just point at the satellite. And that's one reason, one way to get everyone excited. But besides that, for hobbyists, if you're really into amateur radio or ham radio or downloading images from weather satellites, you would need to know when those radio satellites or weather satellites are going to be above you. And when I say downloading image data from weather satellites, I don't mean going to the NOAA website and downloading it there. I mean spending $200 with a makeshift antenna that you point at the satellite, and with software-defined radio, you can download the raw bytes from the satellite and get your own picture of your house from space, DIY Google Maps. Or you can communicate around the world by bouncing ham radio signals. So again, this is the kind of experience in which you would need to know when a particular satellite is going to be over your location. Or if you have a very fancy telescope, you could even take a picture of it, which is what Dr. Sebastian Voltmer did in March 2022 of this year. So this is with an 11-inch CELESTRA reflector telescope, which is very expensive, but you can see it. And this is from about 400 kilometers away. So that's what the International Space Station looks like. And you would need a tool to know when it's going to be above you and where to point your telescope, which is what passpredict helps solve. In a more professional setting, you might want to know, if you are an engineer working for a satellite company or a research firm, and you have satellites in orbit, you need to know when they're going to be in line of sight of your ground station antennas for uploading and downloading your data. And you can use that information to schedule your ground station contacts to maximize overall data throughput. If you have many antennas and many satellites, how to know when to schedule download and upload times to communicate with your equipment. Or if you're an astronomer, you can plan your astronomical observing times to minimize the impact of satellite trails in your data collection. If you have telescope time overnight and you want to look at 4 different things in the sky, 4 different objects, but maybe that satellites are going to cross the path of that object at different times, you can then decide to switch the order of your observing to minimize the impact of satellites cluttering your astronomical data. This is a challenging problem. The equations and methods, you can just derive from physics textbooks or astrodynamics textbooks. And if you know college level or graduate level engineering and physics, you can work them out. But it requires a lot of domain knowledge. When I started working on this project myself, my initial intention was to take different libraries that existed in Python, different open source tools, and combine them together to solve this problem. However, they weren't easily extensible to a more generalized approach. These tools, these satellite prediction algorithms, really in every case, they're very unique to the situation in which they're intended to be used. It's very hard to say change maybe the particular algorithm that you want to use or the different particular satellite propagator that you want to use. There are whole desktop applications, proprietary applications like STK or FreeFlyer that are designed to help solve these problems. But when it comes to open source Python libraries, doesn't really exist beyond just simple implementations of existing physics equations. So I decided to create passpredict in 2019 to have this generalized approach to the satellite prediction problem. And what that approach looks like, or rather what the prediction problem looks like, look at the inputs and the outputs. For an input, you have your orbit data, a location coordinate, and a time span. The location coordinates is easy enough. It's your latitude and longitude of where you're observing from. The elevation is also important, but less so, unless you're at very high elevation, in which that could affect the results just a little bit, but typically your latitude and longitude. The orbit data is, it can come in many different formats, but basically it's the satellite's position and velocity at a certain point in time. The point in time is known as the epoch. So you could think about it as a datetime object in Python. And the position and velocity is relative to an Earth-centered coordinate frame. So you could use what are called like classical orbital elements, or you could just use a position and velocity vector. And then the time span is, the start time and end time for when you want to do the search. That could be 1 day or 10 days or 2 weeks. Typically with a lot of satellite propagators, and just because of the physics of how satellites orbit the Earth, these predictions are only good up to maybe a week or 10 days, depending on the accuracy of your propagator. But you would typically look for a 7 to 10 day time span. And the output would be a list of the predicted passes for that satellite and your location. For each pass, you would have the range, azimuth, and elevation data for the timestamps, for the time points of the results. So when I say range, I mean the distance in line of sight from your location on Earth to the satellite in outer space. So that could be in the thousands of kilometers. The azimuth is just a degree value where 0 degrees is directly north, 90 degrees is directly east, 100 degrees is directly south. This is again from your location on Earth. And the elevation is the angle above the horizon. So 0 degrees is right at the horizon, 90 degrees is straight up, and negative 90 degrees would be straight down through the Earth. So typically when you're doing these satellite predictions, you want to know when the satellite is going to have a positive elevation relative to your point on Earth. If the elevation is positive, then it's above the horizon, you should be able to see it. Although typically in a lot of implementations, you have the elevation be a minimum of 10 degrees in case there's a building or a tree in the way. So just a quick, yes.
Why is the prediction good for only 7 or 10 days? It's like, what's the reason of why it shouldn't be accurate more after?
That's a great question. The reason that it's not as accurate is a lot of these prediction algorithms use what's called SGP4, Simplified General Perturbations Theory number 4. And I don't have the slides about the astrodynamics, but I can talk about it generally in that the satellites typically aren't like firing thrusters. They are, although they do have thrusters and they do use them sometimes, but they typically are just falling, right? So their orbit is determined by gravity. But they're not just having the effects of the Earth's gravity being put upon them. There's also atmospheric drag. Even at the International Space Station is about 250 miles above the Earth, but there's small amounts of atmosphere oxygen, nitrogen particles that it runs into, and that creates drag. And over time, its altitude changes. So in addition, the Earth isn't a perfect sphere. You can't really model the gravity as a point mass. So the Earth is slightly elliptical, almost like a pear. So the gravity is distributed unevenly. There's also solar radiation pressure that affects the satellite's orbit. So to answer your question, the satellite propagation step, where you take a satellite at a certain point and then determine where it's going to be in the future, is complicated. And SGP4 becomes inaccurate fast, where it can be off by a whole kilometer after a few days, and 1 more kilometer inaccurate each subsequent day. So it's considered a low fidelity propagator. Low fidelity meaning less accurate to real world physics. It's not integrating, say, an ordinary differential equation over time. Even though it can be inaccurate to the point of several kilometers over the span of 10 days, the satellite itself is moving at 5 kilometers a second. So 1 kilometer, a few kilometers off, doesn't really matter if you don't need the accuracy of, say, down to tenths of a second or hundredths of a second. And if you're pointing your telescope, maybe your telescope can only point to the 10th of a degree in elevation and azimuth. So if you're an astronomer and are having huge telescopes with micro arcsecond resolution or arcsecond resolution, then you would need a high fidelity propagator. You would need more accurate predictions. But for a general observer or a hobbyist, low fidelity computations are good enough. So that's the engineering trade-off that you go into it.
Okay.
But yeah, that's the answer.
Yeah, thank you.
Yeah, Sam, I have one more question.
Please.
What's the fourth argument in the location? Like Austin equals to location, Austin, Texas. Then I believe that's longitude, latitude. What's 0?
Thank you. That's the elevation. The 0 is the elevation. I believe for this object that I defined, that 0 is the I don't remember if I set it as a default value or if you have to enter it, but that would be the elevation. So yeah, typically for most cases, you don't really need to enter the elevation. If you were to go on Heavens Above, which is a website that's frequently used to find this kind of information, and you enter your viewing location, it doesn't automatically enter your elevation for that point on Earth. If you're in Denver and your elevation is in the thousands of meters or hundreds of meters, it might make a difference. Or if you're on top of a mountain, it might make a difference. But that's what that fourth parameter is. Thank you for pointing that out. So here's this example. We're looking at the ISS from Austin, Texas. Latitude is in degrees north. Longitude is in degrees east, so west longitude is -degrees. And here's this location class that I've instantiated with this TLE object. And TLE stands for a 2-line element, which represents the satellite's orbital data, its position and velocity at a moment in time. This is what that data looks like on CELESTRA. CELESTRA is a very frequently accessed websites for this orbital data for all the unclassified and publicly available satellites that are out there. It's run by Dr. T.S. Kelso, and it's updated. It's updated very, very frequently, so it's highly reliable. The numbers themselves represent like the satellite's inclination, its eccentricity, so how circular the orbit is versus elliptical. The inclination is angled relative to the equator, where it is in its orbit, and the time at which this data is in reference to the epoch. Yes, so this is what the ISS 2-line element looks like, and that's the information that we need to start this satellite prediction problem. Then we create a propagator and an observer to link to our location. in our orbit data. So this SGP4 propagator is in the passpredict library, and that takes the satellite orbital data, this TLE object, instantiates it as this ISS object. And then this observer is what I'm calling the composition between a location object and the satellite object. So you can create these satellite objects and the location objects separately. At this point, for all these steps, we haven't actually done any computation. There's some of the properties of the location object will do some computation if you try to access them, but they're relatively minor calculations. But we haven't done any actual propagating yet. That is done in the next step, which is actually computing the overpasses for the time span. So for this observer object, we're using the Python datetimes to do this, to define our time span. And this pass list method iterates over our observation algorithm from the start to the end time and prints out or returns a list of overpasses. So we give it its start time and end time, and then we can manually set what our minimum elevation is to be, which in this case is 10 degrees. And then this tolerance value is how much we want the pass finding algorithm to not the small time steps, but like where to find the cutoffs for both the elevation and the time points for the pass start and end times. So my goal when creating this website was to have very simple functions that anybody can use that abstracts away a lot of the propagation, a lot of the math, a lot of the physics, that all you have to know is your location coordinates, your TLE data, which you can just copy and paste from CELESTRA, and then your start and end times. It'll give you this list of overpasses. And what this overpass list is a list of predicted pass objects. So here you have the satellite ID number, which for I sort of skipped over that before, but for the International Space Station is 25544, which as I've been developing this library, I just have these numbers memorized now. But every satellite has a what's called a NORAD ID, or a satellite ID number. I think the latest satellites have ID numbers in the 40,000s. And that's how they're unique, and that's how they're typically identified in lots of programs. And the location is also linked here in the predicted pass. And then we have 3 points as part of this predicted pass: the AOS, TCA, and LOS for the acquisition of signal when the pass starts, the time of closest approach, which is the point at which the pass is at the highest elevation, so most directly above you. It might not be directly above you for a given overpass, maybe it's at an angle, but whatever the highest angle is typically when it's the line of sight range is the smallest. So if you were to be downloading data or wanted to know when the satellite would be the brightest, you would want to know, or the most easiest to see, you would want to know when the time of closest approach is the maximum elevation point. And then the LOS, the loss of signal, when the point ends. And there's also an enum type, attached to this predicted pass object to show if the pass is visible, if it's unlit, if it's at night and you can't see it, or if it's during the daylight. Later on, I'll discuss the differences between those. But typically for any satellite overpass, depending on your use case, if you're just like transmitting radio data, then the type of pass doesn't really matter to you, because all you need to know is that it's within line of sight of your ground station, either your professional ground station antenna or your homemade antenna in your backyard. You just need to make sure you could point to it. But if you wanted to see the satellite in the sky, you would only want to look at the visible passes. So a daylight pass is when it's sunny outside, so you can't see it anyway. And an unlit pass is when it's nighttime outside, so you can see the stars, but the satellite is in the Earth's shadow. So you can only see a satellite if the sunlight is reflected off of it. So that is what the visible pass is. where it's nighttime where you are, but the satellite has reflected sunlight. Otherwise, it's unlit. It's in the Earth's shadow. You can't see it. And then for each of those pass points, the AOS, TCA, and LOS, we have the daytime and then the range, azimuth, and elevation. The daytime, in this case, is just returning a Python daytime object. And then the range is in kilometers, azimuth and elevation are in degrees. The magnitude brightness is something that I'm currently working on. This is a little difficult to calculate. This would be how bright it is for the visibility. If you were to look at heavens above to see when, or to see for the International Space Station how for visible passes, the magnitude brightness is by far the brightest satellite that you can see in the sky. But those kinds of calculations are really specific to each satellite, and I'm still working on getting that implemented correctly. But at least the visibility type is I've got implemented. So this is very similar to the pass type, that object. And I created a nice CLI with Python rich, which I love this library. I can't recommend it enough, which prints out this table with the overpasses. So, and I'll go over a demo of this in a second. But here I'm using this my passpredict command for my location, Austin, Texas. I'm identifying the satellite that I want to query for, which is the space station number 25544. I want it over the next 3 days. And I also want to return all the passes, not just the visible passes. So this is what it's outputting. And then for the satellite visibility, you might be wondering how it's even possible that it can be dark outside where I am, but this satellite can still be lit. Well, this is because the satellite is so far in the sky that, and the sun is so big that it's not, it hasn't gone behind the Earth in shadow, which typically occurs during sunset or sunrise. So your location on Earth has just dipped into darkness, either right after sunset or before the sun comes up relative to you, and the satellite is just sort of rounding the bend around the Earth, and it's far enough away from, the altitude is high enough such that it can still, the sun is still reflecting off of it, even though it's dark where you are. So for visible passes, you typically have to either wake up early, 4 or 5 in the morning, or stay up late, 8 or 9 o'clock at night, depending on the time of year, your latitude, and the orbit of the satellite. But that's typically when you would want to look up. So let's get to a CLI demo. Okay, so I have, if you pip install passpredict, you will get this command line prompt. So here we have passpredict. This is using the Python click library, which is also excellent, highly recommend. And you give it a range of options. If you've looked at Heavens Above in the past, my idea was to make this as similar to Heavens Above as possible. So if we want to know the satellite overpasses for Austin, we can, we don't have to give it a latitude and longitude. We can also give it a query string, and the the OpenStreetMap's geocoder is built in, so it'll send out a geocoding query for this location string and return the latitude and longitude internally and do that query on that. So for the satellite, we want to know the space station 25544, and by default,
is there a way to make it a little bit bigger? Like, can you?
Yes, there is.
Thank you.
Thank you for pointing that out. Okay. Yes, so location for Austin, the space station, and let's say for the next 7 days. And by default, it's only going to look at the visible passes. So that's good enough. And there you go. Computing one satellite overpass for 7 days. It gives me the satellite information, my location, for Austin, Texas. And then the TLE data. And this TLE data is automatically pulled from CELESTRA, from that website I mentioned earlier. And here are the passes. I can also add multiple satellites. So another one is the Hubble Space Telescope, which is 20580. It'll just add that. So here you go for the next 7 days, starting tonight. Oh, there you go. So this Hubble Space Telescope should be over Austin tonight at 9:50 p.m. That's interesting. I don't know if you can see the Hubble Space Telescope from Austin because it's not as bright as the space station. And Austin is a pretty light polluted area. But if you were certainly at Enchanted Rock State Park or just outside of town in Dripping Springs, you'd have a good chance of seeing the Hubble Space Telescope tonight. If you are more comfortable with a non-24-hour time, you can do it in AM and PM. And then this is a lot of information. This gives you the start time, the time of maximum elevation, and the end time. But really, if you're planning out a time in which to go outside, all you really should care about is this maximum elevation time. And you want this number to be as high as possible. And ideally, you'd want to know how long the overpass is. So the start time, the end time minus the start time. And then just to find maybe when it begins so that you don't have to get up super early. So I also created the summary table, which just returns for the core components, the maximum elevation and the duration, and then the start time. However, maybe you want to know not just for the International Space Station or the HST, but for all satellites that are sort of known as visible satellites that are bright enough that you can see. Well, CELESTRA has very nice satellite categories already built in. You can see the TLE data for like all space stations, for all radio satellites, for all weather satellites. And so I added that in as a category. And one of the categories is visual satellites. And just for the first day, just for 1 day, we can see how many we can see. So I can tell that,
it's data from? Like it looks at it, but it has to know where a satellite has been in at some point, so you can compute it forward. Where's the data coming from?
Where is the data coming from?
Yeah, like how do you know like even the names of the satellites?
So the names of the satellites, I think you just have to know. So for instance, just from the experience of looking up these things, I know that R/B stands for rocket body. So this is probably like the second stage of a rocket that's still orbiting the Earth. But it's bright enough, it's reflecting sunlight that you should be able to see it. Here, Ariane 40 rocket body, another rocket body. This, I believe, is the Chinese space station, yeah, that's it. This is the Chinese space station. So the data that CELESTRA gets, they are getting from SpaceTrack, which is the U.S., I believe it's the U.S. Space Force, that they publish orbital data for unclassified satellites. And CELESTRA has a special permission for republishing that data publicly. So if you go to CELESTRA, they will have, I can just do that now. Let's see. They will have information on the types of TLEs that are available and how often they get updated. So I believe it is GPE statistics, age distribution. So here is a chart showing the out of all the orbital data, how frequently it's updated. So most of the orbital data, so 19,500 TLEs, are less than 1 day old. No, they're just over 2,000 are 1 day old. And then there's subsequent ones, my dog is in here, that are older. But this data comes from SpaceTrack, basically. And some satellite providers provide their own orbital data. So it gets updated, say, every 6 to 8 hours or every 12 hours, depending on the satellite provider. There are antennas around the world, radar stations that are collecting this information, bouncing radar signals off of the tens of thousands of objects in orbit right now and generating this orbit data and constantly updating it. So that is where the orbit data comes from. And as long as you have the most recent TLE data, the most recent orbital data available, then you can have the most accurate predictions for where the satellite is going to be.
Okay. So you explain where the data is coming from. This is important. And
yes.
And your system downloads it each time you call for something, or is it some it does this the background?
Yes.
Like
so
once in a while. Okay, go ahead.
Yes. So if you wanted to use passpredict as a library, then you would have to provide your own orbital data. You would have to provide this information. We have to give it the TLE. I'm working on making this orbital data, or allowing you to define a satellite's orbit outside of a TLE, maybe just giving it a position and velocity, which would be equally valid, or classical orbital elements, not just this TLE data. But you would need to provide the orbital data for passpredict to know when the satellite is going to be overhead. So this is user-defined information. You would just have to look it up. You can get it from CELESTRA. You can get it from SpaceTrack. You can generate it yourself if you're keen to know orbital determination and you have a telescope and a stopwatch. You could define this information yourself. You could generate it yourself. But typically, you would get it from CELESTRA. The CLI that I built queries CELESTRA for that data and then saves it locally in a file to cache it. So I created I really enjoyed using Redis when I built websites. And so I tried to create like a Redis-like caching mechanism that has a time to live. And so what it will do in the background, the CLI, is it'll look at the cache that exists, determine if it's been downloaded within, I think, the past 24 hours. And if it hasn't, or if it's more than 24 hours old, then it'll just query CELESTRA again for updated data. Excuse me. Similarly, for the geocoding stuff, the geocoding latitude and longitude is also cached in the same way. So that's just using the CLI. But if you wanted to use the library, you have to have your own orbital data.
Yep.
So let's get back to the example. And because we have some DC folks, let's look at Washington, DC. So
how does it translate the Washington, D.C.? Like, how does it know the location? There's like specific locations there that they know by name?
It's using a geocoding in the background. So I could provide the latitude and longitude for Washington, D.C. So if let's see.
I think we lost something. Sam?
Okay. Longitude. I have to give it a negative longitude because it's west. There you go. So unfortunately for DC, I think Austin too, really, is you have to get up really early to see this space station. But on the 25th, if you were up at 5:10 in the morning, you have a very, very good overpass. 79 degrees is almost directly above you. So if you're up that early anyway, just go outside and look to the southwest to see the space station coming up over the horizon. And then it'll disappear to the northeast. Another option for this CLI is if you want all passes, not just the visible passes. Then you get the table with not just the visible passes, but the daylight and the unlit passes. But the visible passes stay green. Yeah, so this is, I really wanted something in which I could just quickly type in the terminal for my location, the satellite, and then how many days in the future I'm looking. And this is what I've developed. So let me go back.
Is there a way to provide a location on the sky and then get in a time or interval of time and then get all the satellites that is going to pass by that location?
To get all the for a given location, to get all the satellites that will pass by a location?
Yeah, by that location. It doesn't have to be precise, of course, but the reason I'm asking is because I'm doing astrophotography. So a lot of times my pictures are getting photobombed by satellites because the exposures are like 4 hours, like 3 hours exposure. So it would be kind of nice to know, for example, like I know I'm going to be able to photograph, at least in theory, if I don't have the clouds or anything like that, I'll be able to photograph this nebula from, I don't know, from 11 in the night until like 4 in the morning. And I would like to know if there's any satellites that are going to pass by that location in the sky.
So you're observing a nebula, an astronomical object.
Yes.
Okay. This is a great point. So yeah, this is a definite issue with astronomical observations, and the way that I have it currently implemented is the propagator. The propagation step. Well, just a quick overview. So the steps involved in computing these overpasses is you start with the orbital data, and then you propagate the satellite for the whole time span into the future, basically. I shouldn't say not for the whole time span, but for a given time step, you propagate the satellite to that point in the future. The propagator usually returns the satellite positioning coordinates in inertial coordinates, an inertial coordinate frame, meaning that it's relative to the center of the Earth, but the coordinate axes are not rotating with the Earth. They are fixed. So the Earth rotates within the coordinate frame. So in that sense, if you wanted a vector at the position of your location on Earth, your topocentric location, it would be changing with time because in the inertial coordinate frame, your vector is changing. But for passpredict, it's I know exactly what you're talking about. The problem is if you're observing a particular astronomical object, you might only want to know a sliver of the sky, right? You would only you don't need to know all the satellites above the entire horizon of where you are, but you only want to know exactly. So the only limitation, I guess, is computational time, right? One satellite for computing one satellite for 10 days for one location, I think it's about 100 milliseconds or 200 milliseconds, something like that. I haven't done a benchmark for it in a while, but the more satellites you add and the longer the time span, the more computationally expensive it is. So I'm looking at solving this exact problem that you're talking about. And the way that I want to approach it is, well, for one thing, it would really only work if for like the following day, for like 24 hours in advance, because there are so many satellites you would have to take into account. It would be too computationally
normally,
prohibitive.
like if you're like doing this for fun, like I do from my backyard. So normally the way I do it is like I usually prepare maybe a day ahead or the same day, but I usually start in the morning. I look on, there's a website called Telescopius, for example, and it gives me like some options that of objects that I could see in that particular night. And then I go and say, okay, well, this might, I mean, this, let's say Orion Nebula might be a nice object to photograph tonight. And then I kind of prepare. I have to prepare a couple of things before I can take like super heavy telescope in the backyard and then like an hour to install it. So, but there's a little bit of preparation. Usually, it's only like I don't know, it's about a day. And maybe either doing that morning or the day before. So so it doesn't have to be like a week ahead. It's just like I can do it that morning when I'm preparing, when I think, okay, this is probably going to be a good day to go outside and take some pictures of the sky. That should be sufficient. If you can do that, that would be nice. I mean, it's not a huge problem, but it would be kind of nice to kind of tell me, hey, at this time, this satellite is going to pass by, maybe integrate with my software and say, don't take that frame or skip that frame. So it's going to save me some time. Because I'm taking, let's say I'm taking like 5 minutes exposures. And then maybe at that time I can say, well, skip this 5 minutes exposure, or maybe reset the time and then to skip that frame so I don't get the satellite into my big 2-3 hour, 5 hour exposure or 4 hour exposure I usually get, because usually in astrophotography you take like 5 minutes, let's say 5 minutes of exposure, and then you use software to stack those like I don't know hundreds of pictures to get like a 3 hour or 5 hour exposure, for example. So that would be nice. I mean, it's a convenience. It's not like it's not the end of the world. I have to deal that with all the time because I have this satellite, like see this line.
Well, it's not just you having this problem with taking your telescope in your backyard. Astronomers are having this problem when they dedicate hours on huge telescopes at observatories. So I would like to make that kind of computation easier. I would like to be able to say, to not just give it, I guess, to not just give this past prediction problem your location and like the time span, but maybe a right ascension and declination in like the celestial frame, right? For the celestial object you're trying to observe, and then say, answer the question, just like you asked, what satellites are going to interfere at what time? The way to do that with the current way that passpredict is set up, you would have to, I guess, use like a bank of satellite data. So maybe all visible satellites or all get 10,000 TLEs. And you would just create one new SGB4 propagator for each TLE and then one new observer for that TLE, but your location would stay the same. And then you would compute the overpasses just for your short time frame. And then you would have, and then append that overpass list to your previous overpasses. And then you would filter back through your list of overpasses and maybe look at ones in which that like the azimuth is wrong for the given time stamp, or the elevation is wrong. Maybe it's in a different part of the sky. I don't have anything right now that allows you to easily transfer from like the resulting fixed coordinate frame to the like celestial inertial coordinate frame. But that is a great use case that I like to support in the future.
If you can solve that problem, you might even be able to integrate with these applications. Like I think one of the most popular one is called the astrophotography.app. let's say it helps you integrate your telescope with your computer and then collects all the images. So that would be the perfect place to have an application, I guess, where you can talk, maybe even can talk to these guys. Again, it's pretty easy. Domain name is astrophotography.app. But if you solve this problem, I'm pretty sure somebody is going to want it because it is a problem. I mean, it's an inconvenience in some way because what you have to do is once you take your pictures, then you have to, before you go and stack them, you have to go one by one. So is there any satellite going through my frame? And then if you do, then you delete it. So it's not a huge problem, but it's still inconvenient.
Yes. So thank you for that. Thank you for that question. That's a great question. But what you would do, and this is what the CLI does behind the scenes, if you're trying to find the overpasses for many satellites but one location, is you're just creating new SGP4 propagators, new satellites, and linking them to a new observer, and then just extending this pass list. And then you're returning the list of overpasses. So the TLEs are coming from the CELESTRA TLE source class that I created to download the data from CELESTRA easily. So it's just getting this visual category, which is the same string that we used in the command line. Yes. So I think pass point information. And yes, just to close up, this is a multi-fidelity problem. So as discussed earlier, there's lots of different components of the satellite prediction problem. There's the propagation, you have to rotate coordinate transformations, and then there's pass searching to, once you have the satellite elevation relative to your location, you want to know, well, when is that elevation greater than 0? And there are many ways to go about finding that. The type of algorithm you use is highly dependent on the type of orbit that your satellite is flying in, whether it's highly elliptical or geosynchronous, or highly inclined or retrograde. That can affect the type of algorithms you use. You can use different propagators, higher fidelity, more computationally expensive, but more accurate to real-world physics. Same with the coordinate transformations from an inertial frame to a fixed frame. And what I would like to do is to break down this problem into those components to be able to have the user pick and choose, do they want low fidelity or high fidelity or mixed fidelity for their satellite computations, and then create tutorials on how to build your own components. Right now, the documentation that I have is in the README, and I'm working on building out more extensive documentation. A lot of the prediction computation behind the scenes uses Python and some C libraries that I like to make easier to use or easier to understand. Or simplify before writing more extensive documentation, but that is definitely in the works. Yeah. So thank you very much, and thank you for that. Thank you for those questions. Yeah, this is my passion project. This is what I've been working on, and I'm happy to share it if you guys want to contribute. This project was highly based on a project called Orbit Predictor, which was built by the same maintainer as Polyastro. And Polyastro is a great Python library for interplanetary orbit propagation and determination and trajectory optimization. Skyfield is another great library. These are all great inspirations. And yeah, I'll be happy to take any questions that you guys have.
Before you take questions, let's thank you properly. There is a button here that does reactions or something, but mute themselves, make some noise.
Thank you, guys.
Good job.
Yeah. Yeah, but please go ahead with the questions. This is interesting because I see people are very, very interested. It's actually a nice discussion. I do have something that bothers me. Can you make an what if scenario? Let's say add a satellite of your own. Can you do something like this and see where it will go? Is it possible?
If you have a satellite of your own, to know where it will go?
No. Like, yes, like let's say I'm launching a satellite that will fly over. I want to know what's its prediction. I want to predict things with your tool.
Yes. So what you're talking about is in the orbit design phase. So if you're designing like where you want to put the satellite in the future, where it will be best suited, what orbit is best suited for it, depending on if you if it's going to fly over your house or the ground stations you have. In that case, you could definitely use passpredict. You would need to have your own orbit determination. So you would need to create your own TLEs to mock your satellite. Because all this is really doing is taking that orbit data, that TLE, and then propagating it into the future. So as long as you can get that satellite orbit data, which is just its position and velocity at a certain time or its orbital elements, then you can mock out where, like how often will it pass over a location on Earth. If you wanted to go more in depth, the orbits are, choosing a satellite orbit is a very definitely a very important step, and it's highly dependent on the purpose for that satellite. So, for instance, a satellite whose goal is Earth observation, so it wants to image all places on Earth, not just areas at certain latitudes, then you would have a satellite that has a polar orbit that goes directly up and down as the Earth rotates like this. So that way it images all of the Earth over time. The International Space Station is at a 51-degree incline, and that orbit was chosen because it can be accessed by rockets that are launching from Florida and Kazakhstan, the Russian spaceport. So those launch sites have the ability to access the 51-degree inclination orbit. So that's why the International Space Station is at that orbit. Yeah, so that's a good use case for like a trade study, a low fidelity simulation of satellite passes for any orbit that you could design.
Okay, so you can do what if, like you create your own satellite kind of.
Mm-hmm. Yes.
Yeah, another application I can think of. This is another hobby of mine, is ham radio. So there's or amateur radio, and there are people that are doing like satellite communications from their backyard as well. So they point the antenna at you. So I don't know how many. I think there are like maybe 100 ham radio satellites that you can track and then communicate and then bounce your radio signals to those satellites. I believe there are already some trackers. I'm pretty sure this track. I haven't tried myself. Some of my friends of mine they were talking to satellites, but this might be another application for that. Maybe to group the ham radio satellites and
yes.
Yeah, and then I don't know. Use it. There's a lot of applications for this that I can see.
Sorry for sharing my screen twice, but yes. So for CELESTRA, one of the categories is amateur radio, and nice. I believe it's just called amateur. It'll tell you
ham radio, yeah.
And if you want all the passes, not just the visible passes, it'll tell you all the amateur radio passes.
Oh, nice.
Yes, and one thing I would like to add to the CLI is a user-defined TLEs or user-defined orbital data from the command line, or maybe to reference a file that you have your TLE data. But this is just from CELESTRA's amateur radio list. SatNogs, I think, is also amateur radio.
Like a list of them? How many there are? I'm curious how many amateur radio satellites are there.
The one, so I don't know the exact answer. And I don't know if these are all accessible. Like these are all the ones that you could use. Let me see. Ones that you would want to use. Here, this is for 90, this found 97. Okay. 97 satellites. And this information just comes from, let's see.
Yeah, I know there's some around like about 100 satellites or so. That sounds about right.
Here we go.
One that I know.
Amateur radio. You just click here. These are all the TLEs. So what this, what the command line interface is doing is going to this file, this URL, downloading the TLE data, and then running the pass prediction for all this TLE data, and then giving the results.
Nice. I'll write this down. CELESTRA.com.
Mm-hmm. So if there were specific satellites that you had in mind, and you knew their NORAD ID numbers, which is this number right here, the first number, you could list those out on the command line, and just it'll take as many as you give it, and it'll do the pass predictions for those.
Nice. Let's see. They're all okay. So they have a bit of different numbers than what I used to, but Geo. Let me see. Geo 32. Let me see if I can find on this website. Geo 32. Okay. I usually have. Yeah, I see like there's NORAD ID. I'm not sure what that is. And then there's the INTL code. So I think it's using probably different kind of code, but see, Zarya. Let me see that one. That's the ISS. Huh.
Mm-hmm. Yeah, Zarya is the Russian name.
Oh, it's the Russian name. Okay. Let me try NOS-44 or PCSAT. Let me see if I can find on this list that I have. It's interesting to see if I can get any of these. So let's see. I think I tried Geo NO-44. Oh, okay, so I think that they have very different. At least the list that I have doesn't match that list entirely. Yeah, neat. Yeah, I'll take a look at this.
Thank you. Yeah, any feedback, please let me know.
Yeah, I mean, there's definitely applications that I could use, especially the astrophotography. That definitely that will make a lot of people happy.
Well,
if you can integrate it with the astrophotography app, which is one of the most popular ones that people use.
I will take note of that.
Yeah. I wrote the let me put it again on the chat. This is astrophotography.app, and this is one of probably the most popular ones. It's a commercial one, but people pay for it because it's worth it. It's very well maintained and works all kinds of cameras and mounts, like telescope mounts. It's like really, really powerful, and it does the job.
Thank you. Yeah, that's. I know that it's a concern with research astronomers too.
Yeah, definitely. Yeah, especially when SpaceX launched a bunch of satellites, and they're still doing pretty much every week.
Mm-hmm. Yes.
Like the light pollution.
You should continue the discussion later on. This is interesting. I do want to give an option for other people to ask questions. So if anyone has a question, please jump in, and I'll check the chat for those who are either shy or. Let's give it a minute.
There was a question from Joe. Is there a way to know which satellites will never pass over a given location based on their orbits? That's a good question. Based on the orbit alone, the easiest thing you could look at is the inclination. If you're in Norway, which is 55 degrees north, depending on what part of Norway you're in. If your satellite is inclined just like less than 10 degrees or at the equator, then you'll never be able to see it. The satellite, just because of the way the Earth, just because of the way gravity works, if you want a satellite to pass over, high latitudes, it needs to be a highly inclined satellite or just really, really far away. So maybe a geostationary satellite. Scott Manley, the YouTuber, has a great video from a few years ago describing how different orbits work and like why you would choose one orbit over the other. But if you're like not sure, if you want to do the computation, you could just run this passpredict algorithm, like run the observer.passlist, and if you get a blank result, then it's not going to pass over you for the next 10 days. And I don't think you need to, you wouldn't really need to go further out than that. If it was going to pass over you, it'll pass over you within 10 days. At least once, even if it's a poor pass, even if it's not a very good pass, or during the day. Yeah.
And this is Joe again. Quick follow-up. Before you joined, we were talking about open source, and for those of us that are new coders and trying to get our feet wet with contributing to open source, and Jacob was saying one way to do that is to take some of the work off the hands of the creator. Do some of the grunt work, the administrative stuff, sorting through documentation or issues. And I'm wondering if you have a need for any of that kind of stuff with passpredict. Is there a wish list of help that you would like as the, I'm assuming you're probably the sole creator of this?
Yeah, this is really my first time. I've shown it to a handful of people, but I haven't really like publicized it that much. And there is a lot of stuff to work on, a lot of new features to add. I welcome contributors. It would probably be most helpful to. I don't think it would be like. It would be hard to accept contributors just without like discussions because the library is changing so fast. Like I'm developing it actively, and so it's not quite in a. Like the code base isn't stable enough so that if you were to like make a change in one area that it wouldn't suddenly like be moved to another area. So I would encourage like communication and coordination when working on these things. But there's definitely even just small items that can be tackled. Like for instance, instead of passing the satellite names in the command line, the satellite numbers in the command line to pass like an argument to give a file for a list of TLEs. And then another thing, instead of TLEs, to have more general orbital data definitions, OMM, and I can't remember what OMM stands for, but the TLE as a format is being phased out because it comes from the days of punch cards when there was a strict character limit. And there's other issues with it going forward, but there's a move towards a more like generalized JSON type approach to that orbit data because it's just fields of floating point values. So that's a great area for contributors to work on. If anyone has experience with like Cython and Cythonizing, that would also be a great help, great input. Part of the work in developing this project was trying to find a balance between ease of use as a user and like speed and execution. So, typically maybe the more general you make something, the slower it might become because there's all these like checks it has to do, and you can't maybe drop down to the sea level as much as you would want to. So I'm trying to make it as fast as possible and as general as possible. So any input or advice or suggestions would certainly be welcome. And if you want to just take it and run with it and create your own thing, that's also okay too. I wanted to make at the very least have like a repository for good ideas on this problem, like a repository for all the types of equations, all the types of math and physics that goes into it, so that other people can just run with it. Because in creating this, I have all my textbooks here, all my physics textbooks that I just referenced, and it can definitely be a challenge to implement these physics equations into Python or into code. So at the very least, I wanted to get those down where it can be iterated on. But contributors very welcome.
The command line, the first few examples you gave us were fantastic. Just a couple of arguments and you get results. So well done.
Thank you.
Oh, any more questions? I see people writing something in the chat. Do you have big plans about geosync satellites? There's only one path and it goes on forever.
That's a good question. So, I mean, in my unit tests, I basically have different, I check the pass predictions for different types of orbits. One of the orbits is geosynchronous. And geosynchronous means that the orbit is far enough away so that as the satellite is revolving around the Earth at the same rate that the Earth is rotating. So if the satellite has a 0-degree inclination, it's at the equator, then it stays fixed at a certain point in space. So this would be like, I think, like Sirius XM or like communication satellites that only have to send signals back to a certain point on Earth, not all of Earth. Those would be geosynchronous. But you could have highly inclined geosynchronous orbits where it's still revolving around the Earth at the same rate that the Earth is rotating, but it's highly inclined. So it goes all the way from like Japan down to Southern Australia. And the path finding algorithms that I've encountered so far in the literature don't always take those types of orbits into account. So that is something that I'm working on, is building path finding algorithms that aren't brute force, but can be used for geosynchronous type satellites, or highly eccentric satellites that don't have easily like parameterized, not parameterized, but like sinusoidal orbits. Sinusoidal meaning the elevation relative to your location is like a sine wave, so it's easy to see and interpret, and or to put like a polynomial approximation over, for instance. So that is definitely a area of ongoing work to support multiple satellite orbits, including geosynchronous. But right now, it doesn't quite work for geosynchronous orbits. It kind of breaks.
Well, unless there's more questions, I suggest we thank you once more and then close the recording, but stick around. Like, we'll be chatting other stuff, but we may be coming back to this. But is it okay with you all that I close the recording?
I got one.
Thank you, everybody.
Oh,
Okay.
wait.
I got a quick question. Yeah. Hey, Sam. I'm just wondering, do you ever make 3D interactive visualizations of the orbits around a globe? And is there a Python package that would help you do that?
I haven't gotten there yet. That is definitely on my to-do list. Polyastro, I'm going to put that in the chat, has some 3D visualization capabilities using like matplotlib. I think if you really wanted to have a good 3D visualization, it might be better to go the JavaScript route. CCM.js is an open source JavaScript library that allows you to basically take it's almost like it's not Google Maps, but it's like if you go to Google Maps and go to satellite view and then zoom out, it kind of looks like that. And you can define orbits and so forth. It's highly extensible. CELESTRA has a CCM.js viewer on their website, and it's really slick. So I don't know, especially for interactivity, JavaScript might be a better course of action than Python for 3D visualizations. Although, lots of cool things are happening with Python.
All right,
so,
thank you.
Yeah, visualization is in Python. If you can do something matplotlib, there's many libraries that like surpass it these days. We can talk about it for later. But are there any more questions, or can we close the recording? Questions going once, question going twice, question going third time. Okay, so we're going to stop the recording, but first, let's thank our speaker again. Let's make some noise. Stick around. We're not going away.
All right, thank you, guys.
Yeah. Okay.